Welcome to ECE 442-542, spring semester, and we'll start as always with some announcements to try to get us oriented or directed in the right place. Most of this information will be on, or a lot of the class information is on the website, D2L, and that's because half of the class is receiving this online, and so I will be recording this. If you're online and raise your hand, I apologize if I don't call on you, but you'll start to get used to it, I assume. There are several sections on D2L that you may start to look at or want to look at. One is the Prerequisite and Review unit or module, and that has many different sub-modules within it. Two on Laplace, one on block diagrams, one on state space, one on Bode plots, one on MATLAB. Those are for review or to see if you haven't studied some of that material in the recent past. You might want to view those or look at certain pieces of that material or that content. Unit 0 is where we will start. That's where you actually, if you haven't seen control at all, there are some readings that you can read on your own in that section or in that module, and it's a subunit in that unit, and it's called an overview of control. And you might just look at one of those or two of those. It's not required reading, but it might orient you to the topic of control. The syllabus is located there, as is the passport assignment, and that's the first assignment into the class, and we'll talk about that in a minute. Homework number 1 has already been assigned, so Unit 1 is now available, and this material that we're presenting now, today, will be in Unit 1 for the class material. There's no class in a week and a half, the MLK holiday, just to remind you. It's not the 14th, it's the 21st. It's not next Monday, it's the following Monday. And there is a reading assignment, and I will use these acronyms: DTSF, Discrete Time System Foundations. That's something that I put together. It has my name on it, and you'll see that in the course resources. You can start reading those 2 chapters before exam 1. You want to be comfortable with that material prior to exam number 1. As I said, here are some of the tasks we want to do today. Sign one of the sheets that's floating around as we're talking today. One that you probably want to look at is, or sign, is attachment number 2, which is the class attendance. We want to talk about the passport assignment, look at the syllabus, and that's actually located in a couple of places on D2L, either in Course Business or Unit 0. Course Resources, that has a lot of material. There's several textbooks, and did everyone receive the email? Did I send that a day or 2 ago about the textbooks and MATLAB? The textbooks, you don't have to buy all of the textbooks, but if you see one or have access to one, it might give you a second set of descriptors, or it might fill in the blanks that we don't have all that much time to cover during lecture. So you might find one of those that you think would work for you and access that either through a library or Amazon. Somehow you might gain access to one of those textbooks that is listed there. Many of them are quite old, and that's why we don't have one assigned for this particular class. What we will be, or what we will use during this semester, I think you'll be able to access in an open source manner. For example, the 2 chapters of the 4 in that Discrete Time System Foundation you have now available to you in the course resources. There's others that are available elsewhere on the internet or on the course website. We'll quickly go over a reason behind this class. Why are we studying digital control today? And then we'll get into system modeling. That should be the wake-up call for how do we start working with a system and modeling it so that we'll be able to control it. And the first part of this, I'm going to be maybe going through quickly, scrolling through, but hopefully it won't be that big of a deal. But I do encourage you to write some stuff down by hand. Draw block diagrams, draw equations, start thinking about what questions you would like to ask, etc. Your passport into this class, which is due on the 20th, the night before you have your vacation on the 21st, just so I can look at all of them on the 21st, since we don't have class that day. State your name, a nickname if you go by something other than John Smith. If you go by Bill and your given name is John Smith, I would prefer to call you by your nickname if that's the name you want to be referred to. Your email, an up-to-date photograph, and this time something to connect me with you is concerned with what's one of your favorite foods. And when do you like to eat it? And what are the ingredients? It may be foreign to me, and so you need to tell me what's in this dish that you like to consume. Then there are one more part to this, and this is a visual description of a book, so if you like picture books, you can click on this link and it will provide you some hand-sketched summaries of each of the chapters in this book. Make it stick. So don't take out your gum and start throwing it at the wall and saying, is this going to stick? I'm going to make it stick. This is how do you make things stick in your mind when you're trying to learn something. There's 8 chapters. I want you to look at those 8 summaries and then say, that one I really like. That one speaks to me right now, and say why it does. That's part 4 of your passport. If you submit the passport into the Dropbox on D2L, that effectively is your signature. You don't have to worry about trying to sign this, scan it if you don't want to, but you can now that we have all of that available to us without much effort. Any questions on the passport assignment? The syllabus should be fairly clear. I have 4 different days of office hours. That's near the top. Here are the notes, the texts, as I mentioned before, these digital control references. Those are maybe a little bit dated, but they're effective at filling in the blanks. Those are not what you have to run out and buy, but you could maybe acquire one of those, and that is what you use to fill in the blanks. If you feel like, I'm not quite sure what he was referring to, there's, I think, 5 of those that you can possibly look at or acquire. The other part that you're probably interested in, but you have to read all of this before you submit your passport. The passport submission is saying that you did read all of the syllabus and you understand the contract. But we have 3 midterm exams. Those dates hopefully will stay as they are. And then we have a final exam. And everyone loves the final exam in this class. It's on the last day, almost at the last time slot for final exams. But this semester, finals are sooner since we're starting sooner. May 9th is the final. It's on a Thursday. It's not a Monday or a Wednesday. And you do have a few times that we break. One is for the MLK holiday coming up shortly. The other 2 periods are the spring recess or spring break in March. This is really the outline of the course, and I'll let you study that on your own time, and then I have a list of about 24 different objectives, and by the end of the course, if you can deal with these concepts forwards and backwards and sideways, then you'll probably be in pretty good shape for the final. So you might just keep looking at those as we progress through the semester and say, oh, these are the course outcomes that are on exam 1. These are the ones that are on exam 2. They're all going to be on the final. The final exam is comprehensive. We won't have 24 questions on the final. We'll have 100. Probably not. You'll probably have 15 questions on the final. You have 2 hours. But for the midterm exams, you will have 75 minutes. We'll have the full hour and 15 minutes that you can have access for your midterm exams. Questions on syllabus, passport. We're grad students, last year of the senior. We've seen this so many times we don't have questions, right? If you have questions after the fact, that's fine. Let me know. Here's the website as me as a student, and if you haven't been there, if you haven't used D2L, it's somewhat intuitive. Hopefully it's more intuitive to you than it is me. But there's a welcome page. That's the course home page. And most of the material that you will be dealing with is found by clicking on the content button. That's right here. And right now, all that we have so far on the website is collected in that outlined version. So after today's class, you should be able to click on Unit 1, System Modeling, and find this lecture with the notes in that spot. All of your assignments will be submitted. And your first one, this is really sort of trying to get you comfortable submitting material into the Dropbox, but your passport will be submitted through that particular Dropbox on the assignment page of D2L. All of your homeworks do have a particular Dropbox folder, or they will when it's due. Right now, the first 2 are available for submission. Questions on any of that material so far? Let's then talk about why we might want to take, or why you might want to take this class. And here's a block diagram you'll be able to do even when you're in the deepest sleep possible this semester, is sketching this controller, system, feedback, interconnected diagram. We'll today talk about how do we find a system, a G of S, or something else. Maybe it will be a state space representation. In this class, it could be a set of difference equations in the form of a state space, but we will be thinking about this kind of a block diagram. But here, maybe we don't want to have a capital D of S. Maybe we don't want an analog controller, and that's because it may be susceptible to many, many different things. Now that you've taken a course, I can tell you this, right? Now that you've spent 1 semester, I wouldn't want to tell you this before that class. Then you'd go, where's the drop box? Drop form. No, you still want to take that class. But anyway, you might have environmental conditions, temperature, humidity, that these parts, the parts that make up that D of S, what do those consist of? What do you think, if it was an analog D of S, this is a quiz on those that took 541 or 441, did we actually build, or did we realize our controllers that we designed last semester? Some of you might have in the project phase, but what makes up D of S? Or what can make up D of S? That controller, the analog controller. Any idea? We really didn't talk too much about it, did we? But if you go over to the stockroom, you could find parts to put together to make a controller. You might have an op amp. You might make an integrator. You might make something that now is a pole and a zero in the form of capacitors, resistors, all plugged around an op amp, and that now is a realization of this D of S. You now have these pieces and parts, and that's what this susceptibility list might be referring to. These parts now get old. The tolerances, maybe you thought, oh, I thought this was a 1% resistor, and in fact it was maybe a 20% resistor, and now you're not meeting your specifications that you wanted to meet. Noise might be entered in the system, and the parameters, it might be expensive. They may be heavy to put all of these parts together onto a circuit board and make your controller. Oh, and now you have to solder. Oh, I need to change something. You need to desolder, resolder, debug, figure out what's wrong. All of those may limit the flexibility that you have with this D of S. So what we want to do in this class is talk about replacing that block with something else. We want to replace that D of S with a microprocessor, a microcontroller, a computer, a digital signal processor, an FPGA. That's what this class is concerned with. How do we now create what we will call a D of Z? Since now we're in the discrete settings, we'll have to worry about Z's instead of S's. And those Z's are not for sleeping, but for the Z transform. But that's what this class is going to be concerned with. We're now going to think about how do we create that capital D sub little d of Z. And it now has to interface typically with the same plant, G of S, that was in the previous block diagram. We're still trying to control the same system. But now how do we create that D sub D of Z? And it will have to be interfaced with the analog hardware, and that's why these A to D and D to A converters are on either side of that particular block, D sub D of Z, which may take some sequence of numbers, manipulate those, work on those with some computations, spit out another sequence of numbers. Well, if you hit a motor with a number, it won't know what to do. So you have to convert that sequence of numbers, discrete numbers, to something that looks more like an analog waveform. And that's what that D to A, the digital to analog converter, and we'll talk about that in this class. It's probably going to be a ZOH. We have a lot of acronyms floating around, but that's a zero order hold. You put in, or you in the left-hand side of that D to A, you might feed it 1.7. Then you just hold that constant until the next sampled numerical value, or the next number in that sequence coming out of your controller, it's now maybe 2. But you've now held that 1.7 constant until you see the 2, and then the clock hits and you say, oh, now I need to put down a 2 until I see the next clock cycle occur. That's what we want to do in this particular class, is figure out how do we design D sub D of Z's to allow us to achieve the appropriate performance and robustness characteristics or control of any given system G of S. And it could be that we have another picture. where we actually have an inherently discrete time plant. It's no longer maybe an analog system. Maybe it's a computer network, and we now have a dynamic model of that, and we can describe that in terms of difference equations or in terms of this transfer function, capital G of Z. Then we don't have to worry about all these A to D's and D to A's. We can just directly interface these sequences of numbers, and we now need to find or design this controller, capital D sub D of Z. That's what this course is really concerned with, or that's what we're interested in this particular course. Now what we want to do is talk about how do we create or find these G of S's. We need to be comfortable with that, and I'm assuming that you know some of that from 320. That's the prerequisite for this class. So how do you get a G of S from some circuit or system? For example, suppose that you now have modeled a system and it is governed by this differential equation. Y double prime, that means the second derivative of y with respect to t, plus 4 times the first derivative of y, plus 13y is equal to u of t, where this y of t is the output and u of t is the input. And if that's the case, can you now write down what capital G of S is based on your 320 knowledge? Pardon? So now what we want is we just want, the question was impulse response. In fact, we just want the transfer function between a generic signal at the input u of t and the output y of t. So this will be in the Laplace domain, and can we get that, or can we connect that if we know this differential equation? What's the order of that differential equation? Second order. We have 2 derivatives, which means what should we be expecting in the transfer function G of S? What does that second order indicate to us? Pardon? It's second order. If something's second order, then we have a second order polynomial where? In Texas, or is that polynomial located in Colorado? Where do we want it? I'm being a little bit silly, but there's 2 places for it to be, right? Upstairs or downstairs in this transfer function. We have a second order polynomial since we have a second order system, and that will occur or appear where in G of S? Downstairs. It now is governing the behavior of our system, and that's in the pole location, which are downstairs in the transfer function, which in this particular case you could Laplace transform both sides of that second order differential equation. And since we're interested in a transfer function, we don't have to worry about initial conditions. We can neglect those, and that's the hard part of trying to figure out how do I recall Laplace transform of a derivative. Now it's easy because we don't have to worry about how those initial conditions cascade or collect when we have higher order derivatives than first. If I now Laplace transform a second derivative, what does that correspond to in the frequency domain? What's a derivative correspond to? A derivative in the time domain corresponds to what in the frequency domain? A multiplication by s. So in this case, over on the left, we would have s squared plus 4s plus 13, and that's actually what we would divide to obtain the g of s. So in the denominator here we have s squared plus 4s plus 13. And upstairs I didn't have any weighting on the input, and that's now just 1. That's now our g of s in the continuous time setting, and we could find that either from a differential equation. Somebody maybe gives us a state space representation. We should be able to find the g of s description for that. We can also do the same thing in the discrete time setting. However, now, instead of differential equations, we're dealing with difference equations. In this class, we'll be dealing with both differential equations, difference equations, Laplace transforms, z transforms. That's what that z is. And we'll start to see all of that as we go through the class. But in this case, now, instead of the s in the frequency domain, we have z's, and multiplication by z in the frequency domain is like an advance in the time domain. So that now, if we z transformed that difference equation, we would actually have, when we z transform little y of n plus 2, we would have z squared times capital Y of z. Then we have minus 0.4z plus 0.1, so that now our g of s here, g of z, is z squared minus 0.4z plus 0.1. And again, we didn't have any weighting on the input term, or the u of n, and so our g of z, if we were looking at this as a pure discrete time system, we would now be starting with the system description of g of z given by 1 over z squared minus 0.4z plus 0.1. This will all become second nature as we work our way through the class. Right now it's like, where did he get that? I don't expect you to know that, but hopefully you can see the correlation between a g of z and a g of s. And again, with the g of z, this system transfer function in the z domain has also zeros and poles. Those concepts will be the same. They'll just mean different things in the complex z plane. We're going to have a lot of complex planes floating around. We'll have an s-plane, a z-plane, etc., and we'll have to understand what those mean and how are they related or connected. Realize that in this class you're going to have to figure out, how do we connect all of those pieces and parts. If somebody gives me a third order differential equation, how can I control that system? Oh, maybe I want to put that into a g of s. You need to figure out how to find a g of s. Now what do we do? Well, maybe now we need to figure out, how do I take a g of s and obtain a g of z from it? And we'll talk about finding discrete equivalence. That could be similarly understood if somebody gave you an analog filter in 320. Did you design filters in 320? The correct response is yes. If you didn't, I'm bummed, and you should be too. But if you now have a analog filter, how do I now use that if I actually am sampling a waveform and trying to get a digital filter? How do I connect this analog filter with a digital filter? I really love this analog filter. Can I now realize it in a computer in a digital manner? Can I come up with a difference equation instead of this analog description of my filter? How do I do that? And we'll do that in this class, and we'll learn how to make the connection between g of s's and g of z's. or D of S and D of Z, etc., using discrete equivalence. That being said, let's go through some modeling, and this is meant as a review in the continuous time setting. This should be familiar to you from a 320 background. And 320, what's the title of that course? Help me, because I have to lecture in it tomorrow. It's electric circuits, I believe, is the title for 320. 320A here. Or circuit theory, but in our class here, we call it electric circuits, I believe. I think that's what I put on the syllabus. I hope that's correct. If not, I'll have to modify the syllabus. But let's now look at the following circuit and see if we can start to obtain a model for this circuit. And I can already see where you might have some issues. That little u of t in this class is not necessarily the unit step. That's just a generic input waveform. And it will take on whatever waveform or signal we want it to be. That's a voltage supply that will be determined by whatever we command u of t or say u of t is. And it's not necessarily a unit step. That's just a control signal, an input. Let me call this R1, this R2. And let me say that I'm interested in the output being the voltage drop across that second capacitor, C sub 2. If I now want to model this circuit, what do you start doing? Or what do you start thinking? Besides your hands being all sweaty and clammy, so now you can rub those on your pants, get rid of that nervousness, and say, okay, now how do I come up with a model for this circuit? And what are some guiding principles that you can be thinking about relative to this circuit? Your eventual model will be, or what will it consist of? Do you have any feel for where you expect to be at the end of this modeling process? Is that question vague enough? What did you talk about up here when you ended up with a differential equation? What was one of the characteristics of that differential equation? Its order. You said, oh, it's second order. Can you say anything about the generic order of this circuit? Is it first order? Is it fifth order? Is it fourth order? I've got 4 discrete parameters, an R1, an R2, a C1, and a C2. I went to the stockroom and picked those up before class, so I want to use them. Do I have a fourth order system then? What's the order of this system and how do I determine that? Do I have any energy storage elements? Yes, the capacitors, and that's what gives you the system order. In this case, you're expecting a second order result. If you end up with a transfer function, you're looking to find maybe a denominator polynomial that's s squared. That's where you're maybe hoping to end up. Well, if that's the case, then how am I going to do that? Well, I think I've told you, maybe not in 441, but in a 320, something that you need to know until you retire. If you're putting that shingle on the board or on the wall that says electrical and computer engineer, BS or MS, then you need to know a few things until you put that in the box at your retirement party or wherever you put it when you retire. This guy's not making any sense at all. What do you think of when you see a circuit that has capacitors? I think I'm hearing somebody's a little bit chilly. So you might think of ice, right? Eli the Iceman. Eli comes to mind when you have inductors. Ice when you have capacitors. So in this case, we don't have any inductors, so we can forget Eli for now, but you don't want to forget him in this class. You'll need to keep track of Eli, and in this case, it's ice, and what good does ice do? Besides, it helps if you have a bad ankle or something else. You want to, elevate and ice that ankle? Where did that come from? It didn't come from a capacitor, did it? But how do you connect ice with a circuit that contains capacitors? What does that acronym allow you to do? Until you retire, if somebody says Eli the Iceman, what does ice give you? It tells you the differential relationship in the time domain connecting the current and the voltage of a capacitor. It says then that if I'm interested in the relationship, the time domain behavior of a capacitor, ice tells me what it is. The current across that or through that capacitor, I sub c of t is now c dv sub c dt. And there is your dynamic behavior. There's your energy storage relationship on this capacitor or these capacitors. We can now use that information to hopefully come up with or create the dynamics, the description of the dynamics of this electrical circuit. We can use ice. And that now is sort of begging the question of how do I maybe get these capacitor voltages in my equations. I would say let's just now start labeling those voltages. There's an x sub 1 of t, and I can now say here's an x sub 2 of t, which in fact is equal to y of t. So if you want the output of this, it's just going to be x sub 2 of t. If we can now find equations that describe the time rate of change of x1 and the time rate of change of x2, we have our second order differential equation, or this description of a second order electrical circuit. And in this case, we can find that one way. I know you guys want to do mesh equations, so that's why I'm going to do node equations. Let's write KCL equations. And let's write them here at node 1 and at node 2. We're adjusting the other node, u of t, and we have a common terminal that connects or relates u, x sub 1, and x sub 2. That's sort of the virtual ground that we've labeled. That's our common node in this electric circuit, which is down here. Everything is referenced to that node. And u, we adjust. x1 and x2 we want to relate based on R1, R2, C1, and C2. If that's the case, and now I'm suggesting that we want to write KCL equations, at node 1, if I can figure out the currents going out of that node, I have now one equation of the two that I need to write in terms of KCL. So let's now write KCL equations. Associated with, or the one at node 1, and that now I'm looking for three pieces to come up with the dynamics associated with a part of this electric circuit. What's the current flowing out of node 1 horizontally in this way that I've drawn it to the left. So now I want a positive current going as I've defined it or as I've labeled it. How do I write the equation that describes that current going from right to left in the top branch, in the horizontal R1?
R1 times the difference in voltage, so R1 times x1 of t minus u of t.
So now I want the current. So now I'm wanting voltages divided by the resistor, right? So now I want that voltage drop. Here's my voltage drop from here to here. And that's now x1 minus u, isn't it? That drop, and then I divide it by R1. That gives me the current going to the left through that branch, R sub 1. Here then I have x1 of t minus u of t over R1, and that's the current going to the left out of node number 1. What's the current going down? Eli? Here's a way to sort of check the other peers that you will encounter maybe during your career. If they give you an equation, one thing to do right off the bat is check the units. Oh, they've got a current plus a voltage. How do they do that? So you don't, if we now are writing an equation, all the units have to be consistent. I need a current plus a current equaling a current. So now I can't put in this equation, I shouldn't have something like that, because that first term is a current. I can't add a voltage to a current, but you might see it. And I might see it on an exam or on a homework, and I'll say, what did I say in the first day? Okay, it's not going to cost you that much. It's not going to cost you your job, which it might if you do it later. So that's why we want to correct that now. Is that clear? I now need to add a current, and I'm saying what's the current going down, vertically down from node 1?
C1 times the derivative of x1.
That's just ice, isn't it? That's why we remembered ice until we retire. That current going down is now simply C1 dx1 of t dt. And that's not x1, is it? That's a derivative of x1 scaled by a capacitor value. And now I need to add one more term, which it needs to be a current as well. The current as I've drawn it, going from left to right, out of node 1, is the voltage drop in that direction, x1 minus x2 divided by R sub 2. This is pretty easy, isn't it? The hard part's when you have to do it on your own, not when you're listening to me tell you. So you might go home tonight, start drawing a circuit and saying, I'm going to do some ice. And then you pour something on top of that ice. No, you want to do the circuit analysis. Don't get too carried away with that ice. Okay? So this is now what? This is whatever I just said, x1 minus x sub 2 all over R sub 2 is equal to 0. That's one of my first order differential equations that I need that model this electric circuit. At node 2, we do something similar. And now I could actually ask you to do that, right? Now you simply say, oh, let me sum the currents leaving that node, and I'm going to do it like I just did before with node 1, using similar thought processing. What's the current going from right to left horizontally through R sub 2? And you can now write that down, I hope. this is now going to be x sub 2 of t minus x1 of t divided by r sub 2. That's the current going out of node 2 from right to left horizontally. Now I just add to that the vertical current going down, and that's ice again. I just have to keep track of the right capacitor and voltage. So this is now plus c sub 2 dx sub 2 of t dt equaling 0. There is my second order system. It's a set of first order differential equations. There's my second order system. What's my output? In this class, we usually call our outputs y's. Y of t is now the voltage dropped across that rightmost capacitor. The output then, if I can now figure out how x1 and x2 evolve in time, and that's possible from these differential equations, all I have to do is look at x sub 2, and that's now the output. That's what's happening at the output of that circuit. And do you see that we could have created a second output or a different output? I could have said, I actually am interested in the current flowing through R1 from left to right. I could have said that's my output. Or maybe I want the output to be x sub 1. Or maybe I want it to be a linear combination of x1 plus 7x sub 2. That could be an output. Maybe I have two different outputs. x1 is one and x2 is a second. Maybe I have two outputs in this system. If this is now my time domain description of the system, input, two state variables, and output, can I build a block diagram that does the same or describes this same set of dynamics? Did you learn that in 320? Does this look somewhat familiar from 320? Was that too long ago? Well, now you get to remind yourself of what you learned, or were supposed to learn in 320. Let's now look at a block diagram. And since we have the description of the system in the time domain, let's look at it in the time domain, and in particular, this is going to be an all-integrator. Block diagram. How many integrators do you think we're going to have in that system, in that block diagram? We're going to have two since it's second order, and we have two first order differentials. We have a dx1 and a dx2. If we integrate those, we're going to end up with x1 and x2, and that's really what we want to keep track of. This all-integrator block diagram then is going to be consisting of two integrators, and now we simply need to interconnect those integrators somehow. Which one? Let's look at from the second equation. If I now feed in to this integrator and I make this x sub 2 prime of t, what's going to come out of that integrator? Just the integral of the derivative, so there's x sub 2. Well, that was pretty easy. So let's do it with the other one. Suppose I now say this is x1 prime of t. There's now x1 of t. I now build this up, I interconnect this based on how these differential equations are described. If I solved that second one, this will be easier. If I solve this second one for x sub 2 prime, do you see that I move those other two terms to the right-hand side and I divide by c sub 2? Sitting on the right-hand side, I now have x1 of t scaled by what? Do you see what I'm trying to say? I'm trying to say that this equation leads to x2 prime is now 1 over r2c2 x1 minus 1 over r2c2 x2 if you solved that for dx2 dt. I now need to make that x2 prime signal in my all-integrator block diagram a linear combination of those two terms on the right. Or I now need to scale x1 by this 1 over r2c2 and add that to a negative 1 over r2c2 scaling x2. And here's x2. I pull that down, scale it with that weighting, and now I've built a connection for x2 prime. And I can do something similar for x1 prime. It's maybe has a few more pieces to it, but now you could do the same thing up here. You could solve this for x1 prime, so divide everything, all terms by c1, c sub 1, and solve for x1 prime. And I hope you can see that you have something scaling in x1 on the right-hand side, something scaling in x2, and something scaling the u. If we put all of those pieces together, and this is something you can check at home tonight, is now you have 1 over r1c1 scaling u of t. We have something weighting x1, and that something is minus 1 over c1 times 1 over r1 plus 1 over r2. And we have something coming from x sub 2, and that something is 1 over r1c1 and there now is our block diagram, and this is actually our output y of t. So if somebody now builds this circuit, go to the stock room, get some op amps, create some integrators, interface those with some gains. That's what these 1 over r's and c's are. Those are just gains. And now somebody wiggles u, puts in some waveform. All this integration, interconnected stuff, this all-integrator block diagram, will spit out y of t, which is the voltage across c sub 2 of t, in real time. This is actually an analog computer. So now you can go home and say, yeah, I can build an analog computer. And they're going to go, why do you want to do that? Well, now I can solve differential equations with an analog computer. Has everyone seen this in the ECE building? The analog computer that's in the ECE building. The next time you're in room 530, look at the back wall, and there's a picture of an analog computer. And it essentially is a box that has a bunch of wires that you can interconnect with gains and integrators. Do you see that if you could build two integrators, some summing junctions, and some gains, you can now create a differential equation solver? Don't you wish you were doing this in DiffyQ? To solve those differential equations, now you can just draw this diagram and say, here's my solution, sir. F. But you now have a way of solving second-order differential equations by using an all-integrator block diagram. Can we now take that into the frequency domain? We want a transfer function. This is a time domain description of our system. That's consistent or equivalent with that set of two first-order differential equations. This gives you the same description of that set of equations. Now somebody says, well, I really want to talk in the frequency domain. I want to live in the frequency domain. I want to see a block diagram in the frequency domain. Can we now convert this into something that's equivalent, but now instead of in the time domain, it's in the frequency domain? And now we want to be thinking about these integrators as operators in the time domain. What do those operators correspond to in the frequency domain? 1 over s. We differentiated by multiplying by s. We do the antiderivative or integrate by dividing by s. Which means then down here we simply have two blocks that replace those integrators, and those two blocks are 1 over s blocks. And because I'm going to get lazy, I'm going to actually say, suppose that I call this mess of coefficients alpha sub 1, 1. And this coefficient alpha sub 1, 2. This one's alpha sub 2, 2. And this one is alpha sub 2, 1. And let me just call this coefficient beta. Are we okay with that? Now I can draw the block diagram in the frequency domain has exactly the same structure. It's just now these integration operations are replaced with blocks that are 1 over s blocks. Where now I have, coming into this, I have a beta gain. There's the Laplace transform of that input signal, so that's now u of s. Here I had an alpha 1, 1. And I also had a alpha 1, 2. Making up this particular location, but the output of this is now the Laplace transform of x sub 1 of t, which is now capital x sub 1 of s. Here is the Laplace transform of x sub 2 of t, which is x sub 2 of s, or that's now our Laplace transform of the output y of s, and making that up is this linear combination of a weighted x sub 1, and this was weighted by alpha sub 2, 1, and alpha sub 2, 2 then squeezes in there. This is now a block diagram in the frequency domain of the same circuit. And if you know block diagram algebra, you can find the transfer function between u of s and y of s. And that would now give you a g of s. How else can we model this? Like I said, we want to get comfortable going back and forth with all sorts of descriptions of a system, so that depending on what you are given or what you're deriving, you can now start to analyze and control that system. Another model that we will be working with will be a model in the form of a state space representation. And if we use those same alpha coefficients, we are now simply putting in to a matrix structure or formulation those first order derivatives that we had before, x1 prime and x sub 2 prime. That's what that, it's not very big, but this is now an x sub 2 prime. In terms of the alphas, so that I don't have to write all those r's and c's and ratios, this is now alpha 1, 1, here's alpha 1, 2, alpha 2, 1, alpha 2, 2. Those scale x1 of t and x sub 2 of t. And now how does my input in this particular system, how does my input influence the time rate of change of x1 and x2? How does U influence x1 prime and x2 prime? Do you see that x1 prime has a piece that's simply beta times U? Does x sub 2 prime have a direct connection to the input U? Is there a signal coming into that rightmost summing junction directly from the input U, scaled and going in to create a part of x sub 2 prime? What I'm asking, do you see something going like that? Is it there? No, it wasn't, was it? It wasn't present. So we don't have a direct connection into x sub 2 prime, which means that down here, that's a 0. We do have a piece that feeds from U into forming part of x sub 1 prime. This is now our state space representation. We will call this our system matrix and probably refer to it with a capital A. Here is our input matrix, which will be referred to with a capital B. And now we want to connect all of these to the output y of t. And y we want to be some linear combination of x1, x sub 2, and u. You've already told me what y is in this case. What was y? It was just x sub 2. So now we need to put together the equations in such a way that they combine x1, x2, and u to give us y, and y is just supposed to equal x sub 2. Is there any weighting of u in our output equation for y? Does u explicitly come in? No. So that's why this matrix, it's a scalar, it's a 1 by 1 matrix, will be 0. And how do we now multiply a matrix here that we can call C? This is our output matrix. This is our D matrix. When you're learning our ABCs, you maybe don't want to communicate that to mom and dad when you go home. Yeah, we spent 75 minutes learning our ABCs. Oh, and D, our direct feed-through term. But here we have a 0 for the direct feed-through matrix. What's the output matrix? What are the dimensions on that output matrix? How many outputs do we have, or did we identify in this system? Just one. So this particular right-hand side better just give us one equation, so it's now one row tall, all of these matrices. How wide is the C matrix? 2. It has to be compatible with the 2 by 1 state vector, and we want it to eventually pull off just x sub 2, and we can make that happen with an output matrix C equaling 0, 1. Now my moment of truth. What if I wanted to circle back and connect this state space representation with a transfer function? Or can I create a transfer function from A, B, C, and D? Now I should be looking at all of those students that took 441 and 541, and they should be getting out their pom-poms or something to start a cheer. Because we learned to cheer in a previous semester to connect A, B, C, and D to the transfer function g of s. Now, don't ask me which cheer it was. We didn't learn very many. Took us all semester to learn 3 cheers, maybe. But how would we connect A, B, C, and D to the frequency domain? How do you go from time domain to frequency domain? Anybody can answer that, I hope, if you've taken 320. How do we go from time domain to frequency domain? Laplace. When we have continuous time signals, which is what we have here. So now if we Laplace transformed this system, what we can do is we can now say, oh, my state vector, I'm just going to label as a single variable x. Yes, it's tall. It's made up of 2 components. But later on in the semester, it might have 4 components or 10 components. And we may just want to simplify it and call it x. So here we have the first derivative of our state vector, x prime. That's a x of t plus b u of t. Y of t is equal to c x of t plus d u of t. And there is now our state space representation. If somebody says, oh, for this particular circuit, can you tell me what A is, what B is? And now you can. You can put that in. A is a 2 by 2 matrix. B is a 2 by 1 matrix. C is a 1 by 2, and D is a 1 by 1. But in terms of this ABCD description, if we now Laplace transform that, since you told me that that's what we could do to get into the frequency domain, how do I Laplace transform this system of equations written in a matrix way? What happens when I Laplace transform a derivative? It's multiplication by s, and I could have initial conditions, right? But since we're worried about a transfer function, we can neglect the initial conditions, and that's what we're doing here. So we want to actually convert this from the time domain, state space representation, into the frequency domain. And if we want a transfer function, we actually can neglect the initial conditions as a result. So we can neglect initial conditions because we are interested in the transfer function. If I Laplace transform a derivative, that's now multiplication by s. And in general, I would subtract that initial condition. We just said we don't need to worry about that because we're dealing with an initial condition. But that x at 0 minus, that's time t equals 0 minus. And this is this tall vector of x sub 1 at 0 minus, x sub 2 of 0 minus. And the capital X is likewise stacked components, an x1 component and an x2 component. Now I need to Laplace transform the right-hand side, and A, in this linear time invariant case, A is a constant matrix. That factors out of the Laplace transform. Meaning the right-hand side is going to be A times capital X of S plus B times capital U of S. S is a scalar. That's our frequency variable. That's a complex number. I can't really combine this with a 2 by 2 matrix directly. I can make that combination if I insert an identity matrix that's 2 by 2 that's the same dimension as that A matrix. Now I can combine these terms that have a common capital X of S. I now have Si minus A X of S is equal to B U of S. I'm going to want to isolate the frequency or the Laplace transform version of my state, and I can do that by multiplying both sides of that earlier equation by the inverse of that Si minus A matrix. And I'm almost home. I can now Laplace transform the output equation and if I simply take this formula for capital X of S and replace it in there, I now have Y of S is equal to C times Si minus A inverse B U of S plus D U of S. And now I have my cheer. I have C times Si minus A inverse B plus D all times U of S there is my transfer function. So if I give you an A, B, C, and a D, capital G of S, the transfer function, is found through this manipulation. S is a complex frequency variable, so you'll have S's sprinkled around, but you will end up with, in this case, we had one output and one input. G of S is a scalar transfer function. It will be a numerator polynomial divided by a denominator polynomial. And after all of this math that you could go through, what would be in that denominator polynomial? A second order polynomial in S, since we had a second order system. And our A matrix A was 2 by 2. I'm guessing you have a lot of questions. We're out of time, so you don't get to ask them. But what you can do is start to think about these concepts, these ideas. We will start to go through these a little bit more slowly in the semester in front of us, but hopefully you can see that we're going to be playing a lot with transfer functions in the transfer functions, time domain differential equations, difference equations, etc. Get ready. We're ready to go for 442 and 542. I'll see you Monday.